Hello everybody. Today we will take a look at tasks of classification. We will discuss DOMIC. It is the geometry object that we want our model to predict after learning process. For this kind of task, we need a couple of models. Math model to use mathematics. Random model to use random. NumPy for matrix and tensor calculations. Matplotlib PyPlot for visualization. Torch for our learning process. Torch Artegrad. All Torch is for our models, our neural network. So after that, we need to specify device. Okay, now our device is, let's take a look. CPU. Okay, nice. We will look at CPU now. Let's repeat what we need to start learning. So we need dataset, that's why we will generate it at the beginning. Then we will use fully connected layers, only them today. Then we need activation function for adding non-linearity to our models. We have learned 3 variants of activation functions. Not 3, we learned 5 variants, but today we will use only 3 one. ReLU, leaky ReLU, and sigmoid function. We will use loss functions to calculate the correct direction of our learning process. We will use MSA and cross-entropy loss as loss functions. And we will use today optimizer for calculating these losses and the steps of our weights for high quality learning process. We will use SGD optimizer and Adam optimizer. So let's start. We will start with the first one, with dataset. We inherit our class DOMIC dataset from class dataset, which is the default basic class in Torch. Then we need to write what kind of parameters will lead us to the creating of geometric object DOMIC. And then we need to specify every it part. So left truth, right truth. You will see it a bit later. All is good. Okay, generate is also for generating points of this geometric object. There will be 2 classes of points. Classes that are inside this geometric object and the second kind of points that are outside of our DOMIC. And then we need the function show that will visualize us this geometric object. Then, of course, we need method len that will return the length of our dataset, as we have already learned in the previous seminar, and method getItem for taking an object with an index from our dataset. Okay, let's define it. Cool. Then we need a train function. Train function for predicting this model, with predicting this geometric object with our model. So here we can see 0 the gradient buffers, then we see samples, our dataset, then output, the resulting of our network values, predictions, calculating loss with criterion, loss back propagation, and we need then to update our values of weights. Okay, let's do it. Nice. And then we need test function for evaluation of our model, for testing how good does it work in other data. So we want a dataset that consists of 5,000 points. I think it's okay. We doesn't need more points for these tasks. So our DOMIC looks like this one. Yes? It's like a house. Roof, right roof, left roof. Okay, nice. Then we need to write our own class of neural network, and it will be inherited from the basic Torch model as each class of neural network that we will use. Here we can see two basic important methods init, where we can see layers that will be used in this model, and forward in this function we can see an architecture of our model. Then we specify the device. Our device is CPU. And then I want to print net for visualize the layers. Okay, here we have two neurons as input and one neuron as output. Bias is true. Here we have one fully connected layer, and let's try to train this model for predicting this complex geometric object, DOMIC. We will use epochs for increasing the volume of dataset, for increasing the steps of learning process, for increasing the quality of our training process. We will need criterion, loss function, we will use MSE loss, and as optimizer we will use SGD with learning rate equal to 0.1. Okay, let's train it. We are working on CPU now, and you can see that the training process requires a lot of time on this device. If we will use GPU, here the process will be more quick. Okay, nice. Let's look at loss function. So our loss function decreased through the learning, and that's what we want. But so as you can see, the values of loss function decreased a bit, and there is not what we want. So the training is bad here, and we can test our assumption. Yes, you can see that it's not what we want. So let's take a look what we can do here. But of course, the problem is not in our parameters. The problem is in architecture of our model. This geometric object is really complex. We need more fully connected layers to predict it. Let's change the architecture of our class net. We were using model with only one fully connected layer, and now let's use the model with two fully connected layers. And the hidden layer will consist of 10 neurons. Okay, so for nonlinearity we will use activation function Licky-ReLU. Okay, let's look how it trained here. You can see that it's really cool. So the loss values are smaller than it was in the previous try. Okay, let's look at loss function. So it's really decreased through the learning. It's what we want. And let's take a look at the test. Wow, it's really more better. This kind of neural network architecture give us an opportunity to predict this geometric object with high metrics. So we use metrics named accuracy. We have learned this metric in the lecture. So here, these metrics give us a value equal to 96. It's a good result. Okay, but let's for example change Ricci-Relu to sigmoid function. And look at results of training with this architecture of neural network. You see the loss decreases, yes, but much more slower. But it decreased. And the result was nice too. Okay, loss function. Nice, yes. So with Ricci-Relu, we get this prediction. Let's look at the same test on a neural network with sigmoid. 93 here. 93 is the value of accuracy here, and it is smaller than in the previous example. And the DOMIC here is predicted worse than it was predicted by Ricci-Relu function. Nice. What's more, we can look at, for example, how learning rate affects on the training process. Let's make it smaller and take a look at our training process. Oh, I need to, one moment. I have not doing, wait a second, 0 grad, I didn't do it. Okay, I should do it here. So, okay, let's look. Nice. Okay, yes. Now we start from the very beginning. It says the loss. The loss is really big at the beginning of the learning process, and it tells us that the weights values were unlearned at the beginning. Okay, here we can see a loss. So with the lower learning rate, our model doesn't train at all. Let's look at test. So here the result that we get it with the learning rate equal to 0.1, and now with learning rate 0.01, the result is equal to this one. You see, it's really bad. It's really, really bad. I don't think so, but yes. Okay, the reason is that the learning rate is too small. We need to do it bigger in this type of task. Okay. And then I want to talk about DOMIC with window dataset. You can see how it looks like here. We will take 5,000 points, as in the previous example, for dataset, and look at this. Yeah, we can see here a house with a window. This variant is more complex than the previous one. We should use the neural network with 3 layers for extract non-convex disconnected areas. Let's try to do it with 2 layers, but I can say you that it will not work, but we can try it. Okay, let's look. The loss decreased to the value of 0.12. Let's look at test. Okay, you see, it's not a house with a window. And this result was getted because we apply the neural network with only 2 layers. Here we need to apply 3 fully connected layers. And look at the result if we will use 3 fully connected layers. I want to add that we don't change any params of our learning process. MSE is MSE, optimizer is SGD, and learning rate is 0.01. And in this variant, in this way, the loss is decreased. You see, it has a really small value. The graph is really good for our loss function. And let's look at test. And here, let's look at another cell. Okay, nice. You see, it's a really good result, and accuracy is equal to 93. Main point is to understand how the number of layers affect to the result of our model, which geometric objects may be predicted with 2 fully connected layers neural networks or 3 fully connected layers networks. Okay. Here we need to use 3 fully connected layers networks. Let's for example change the learning rate, make it slower. We need to start from the very beginning, from the okay, nice. Loss is decreasing loss is decreasing slower, you see? In this way, it can stagnate in the local minimum. It's not what we want. We need to increase learning rate value for going and finding the global minimum. Let's look at the results. We can compare it with this one. So you see, it's not what we want. We need a big learning rate. But for example, if we make it really high, it's not good too. We need to select the most correct learning rate, and we may do it only after some tries. Okay, you see, loss is really bad here. Really, really bad. Okay, let's look at the result. Oh, bad, really bad. Okay, let's select learning rate equal to 0.01 and repeat our training process. Okay. 20, 15, 13, 13, 13, 12, 12, 12, 12, 12. It should decrease at the end. 11, 10. And then we just continue our training process, because I think that 20 epochs is not really much. Yes. I was right. All is cool. 7, 6, 6, 6. Should decrease to 5. I know it. Yes, 5, 5, 5, 5, 5. Okay, I think that it's already a good result, but we need to test it at the end of our training process. Well, and it will be 4. Yeah, 4, Kai. Cool. So our loss function is really nice here. You see, it decreases, and the test will be good too. Not really, but good. Yes, it is the best variant we have seen here. So there are some parameters that change the quality of your training process. And number of epochs, number of iterations, learning rate value, choice of loss function, choice of optimizer are among them. So after fitting these params, after adjusting them correctly, you will get the high quality training process. So that's all I wanted to say. Thank you for your attention.